the organizers for the invitation in this very nice conference. I think it was very stimulating so far, and me personally, I've learned a lot. And with my talk, I would like to add a different flavor to what we've heard so far. In contrast to Andreen, I'm going to talk about electron-spin resonance now. But many principles will stay the same because we do inductive detection, and what I will show you throughout my talk is how we actually go from a conventional ESR to a so-called quantum ESR spectrometer, where we push the limits of sensitivity with our ultimate goal to reach single spin sensitivity. And just a short recap in a cartoon style of what we've seen actually in the previous talk already. So how is magnetic resonance working in general? So you go out in nature, you find some crystals, some material, and lots of these materials have unpaired electrons, and these unpaired electrons give rise to a spin. So you have lots of these spins in these materials, electron spins in my case, and those electron spins are a sensitive probe to the local chemical and local magnetic environment. So we would like to read out those spins to learn more about our material. And the normal strategy is you put those spins in a magnetic field, you align all of them, and then you spectroscopically probe them by sweeping a microwave signal, and as soon as you are in resonance, the spins will absorb the energy, they will start to precess, and as you have a precessing dipole, every precessing magnetic dipole will emit radiation. So what you see is that these spins will lose their energy in this simple picture by radiation, and this is inductively detected by the same coil and gives rise to this free induction decay we have seen so in the previous talk as well. So the problem here is that, of course, the magnetic moment of these spins is very, very small. So you need many spins in order to accumulate sufficient signal. And this is really a major problem. And we would like to improve the sensitivity because this is such a nice and versatile method, because you just need some microwave and some magnetic field, and you can study a variety of materials non-invasively. And so many people have thought about how to improve the sensitivity, and the major solution was to just switch the detection mechanism. This inductive detection is very insensitive because you are detecting really small microwave signals which are emitted by the small spin magnetic moments. And so, like one of the most famous examples we have seen it in many talks is the NV center, where you just, instead of detecting microwave radiation, you drive an optical transition, and this gives you a photoluminescent signal which is depending on the spin state. And another method which is heavily used here in the community is, of course, scanning probe, where you use a very floppy cantilever, and you look for like single spins, and there you can actually reach single spin sensitivity for electron spins. And a third method is to use an electrical readout. So here in this example, what you have is you have a spin buried here, and then in this gate structure here, what you essentially have is a spin-dependent tunneling, and this is the way you can read out your signal. But we want to come back to the old inductive method, which has worked so well for the years, and have a look if we can actually boost the sensitivity of the signal by using the toolbox of circuit quantum electrodynamics and all these advances which have been made in the field with microresonators, superconducting structures in general, and quantum limited amplifiers. And just to set the stage a bit, what we are going to talk about, so in this plot I basically want to picture the spin sensitivities of different experiments, And what you see here is the noise photons, and here I plot the signal both on logarithmic scale. And so the first thing to consider is there will be actually a fundamental limit to the noise in all the experiments. Yeah? Normally the noise is limited by some thermal motion, but ultimately if you cool down your sample, you will hit the quantum limit of noise, which then is only then limited by the vacuum fluctuations of your sample. And a commercial spectrometer, ESR spectrometer, operates around here at room temperature, and you need about 10 to the 13 spins to get enough signal in a single shot. And now, when you cool down your sample, for instance, to 1.7 Kelvin, we have seen that in Andrin's talk. The same thing applies to electron spins. Of course, you can increase the polarization. In this example, they go also to smaller structures, so they confine the magnetic fields, which give them higher sensitivity. And then finally, in the work of Audrey Bienfait, she was the first to actually demonstrate operation of an ESR spectrometer at the quantum limit. She just finished her PhD in our group. And so there we have a sensitivity of 2,000 spins in the single shot to give us enough signal to detect the spin echo. And
just a quick question.
Yes?
What's the quantum limit at 0.25 and not at 1?
Yeah, so what you usually do in all these experiments, what will come actually in the next slide, is that you are working in a cavity. A cavity has vacuum fluctuations, but then the spin echo signal, which is the actual signal we look at, is only on 1 quadrature. So what we are looking at is the noise on 1 quadrature, and this is then basically encoded here. So normally you have like half a photon of noise in energy, and then if you only look on 1 quadrature, you get to this number here. And so in this talk is basically we build on these experiments here, and this is basically our recent improvements in our samples, where we now go to 300 spins. And before I continue this, let me focus your attention on this small spot. The quantum limit is not a solid barrier. Yeah? You can actually go beyond the quantum limited by using squeezed light, for instance. I don't want to talk about this, but we have a paper on that published recently. So, and now we are at a level of about 300 spins. So as Andrin said, inhomogeneous broadening is a problem, and it's especially a problem with electron spins. Electron spins have a larger magnetic moment. They are less well isolated from the environment, so they will see much more their local environment, and therefore the frequencies will spread much larger. You have strain effects, Hans Hübel has talked about this, which is especially dominant also in our samples. So in the normal experiment, you put your sample inside a microwave cavity to boost your signal a bit. You polarize it in a magnetic field, and then you apply the pi pulse, pi over 2 pulse. The spins start to dephase, and then you invert the time evolution by applying the pi pulse, and then after that the spin come back into phase and finally emit an echo. And so what I want to discuss in the following is how can we now improve this very simplistic scheme in order to improve our signal. And basically there are 3 points. The first one is polarization. That's very straightforward. We go to low temperature. The second thing is the cavity. We can engineer the cavity to improve the couplings. And the third thing is, of course, the detection. These are very, very small signals, so we have to have some fancy detection scheme not to add additional noise in our detection scheme. And so this is the recipe to do so-called ultimate ESR. So low temperatures, this means in our case we go to 10, 20 millikelvin, where all the spins are polarized at the frequencies we operate at, which is about 7 gigahertz. And the second thing is, of course, at these frequencies you don't have any thermal photons left, so the only noise you are left with are quantum fluctuations. And then the second ingredient are these microwave resonators, which come from circuit quantum electrodynamics. So typically people have been used these big, like centimeter size microwave cavities, 3D microwave cavities, and what we do now is we use these planar structures where which are essentially LC resonators, where the active part is this short inductive wire, and then the spins are directly implanted just below the sample, some 100 nanometers below. And therefore we can shrink considerably the mode volume and therefore increase the coupling. And the third ingredient is that we have a quantum limited detection chain using these so-called Josephson parametric amplifiers. And what they allow us is essentially to have a noiseless detection chain. And I will explain how this works. So just again to illustrate a bit where we at. So what you see here is the number of noise photons on a single quadrature. So why single quadrature? Because the echo is always emitted with a specific phase. So this is the only source of noise which interests us. And here you see the temperature. And so this is basically the quantum limited of noise. And when you go to millikelvin temperature, you are in this region here. So so that basically you have no further thermal fluctuations. Now, this is the Josephson parametric amplifier, and this device has allowed us to actually reach the quantum limit of sensitivity, because it allows us to have a noiseless amplification chain. And what it is, what you see here is essentially you have an LC resonator, you have the capacitance which is distributed here and here. This is the inductive part. This here is a coupling capacitor, so this device is operated in reflection, so you send a signal and then it's reflected, amplified. And the important ingredient here is these squid loops here. So the squids have an inductance which depends on the flux which goes through the squid loops here. And by this and this coil here, we can now parametrically pump this resonator, so basically periodically change the frequency, and if we change it at twice the resonance frequency, we have the parametric resonance condition, and then we achieve amplification. So essentially it's a bit like the child on the swing. You have to change your center of mass with twice the resonance frequency of the swing in order to pump energy into the system. And this is essentially the circuit. So our ESR system is somewhere here. The signal travels through this circulator, bounces off here, and then is amplified. And what we usually achieve is about 20 dB amplification, which is enough to overcome the signal to noise of the next amplification chain, which is a Hammond amplifier. So that means that the thermal noise from 4 Kelvin of the Hammond amplifier does not really contribute, and we can actually say that the noise or the signal to noise just dominated by this superconducting device here. So the frequency of our signal is about 7 gigahertz, and so the pump frequency has to be 14 gigahertz. Yeah, so you have two microwave sources which are linked to each other. This is important, so that you have a phase relation between those. And yeah, so one at 7, one at exactly twice the frequency. So now you could ask the question, okay, no thermal noise is great, but what about the quantum noise? Because normally when you think about amplification, what is amplification? Amplification is you take a quantum state which comes from your system, maybe a single photon or something like this, and amplification means you copy that. But quantum mechanics does not allow to copy a quantum state. A quantum state is basically amplitude and phase, or we usually like to talk in quadratures x and y. So every time you try to blow up your state by amplification, you have to pay a price. You have since the quadratures do not commute, you add another half photon of quantum fluctuation. But there's a trick to overcome this. So basically, so here we have our signal with an amplitude in the phase, and just rotate it here on the I quadrature. And now here, these are the vacuum fluctuations which come out of the cavity, of the ESR cavity. We cannot avoid them. And then when they go through this amplifier and we pump at twice the frequency, so like this 14 gigahertz, and we adjust the phase in such a way that the signal and the pump have the same phase. What the amplifier does is it does not just amplify the signal, but it actually squeezes the signal. Yeah? So if you are in phase with your signal, you get an amplification. If you are out of phase with your signal, you get a de-amplification. Yeah? And so if you squeeze a signal, you don't add noise. Yeah? Because the area of this blob does not change. You just change it, deform it into an ellipse. And this is why we don't add quantum noise here. So for our purposes, we work with an amplification on the order of 20 dB. But I have to say this is not perfect squeezing. Yeah. So we did squeezing experiments where we squeezed, I don't know, like 5 dB to 10 dB. But then there's really a limit. And the limit comes from the fact that you use the squid. And the squid is not a linear inductor, but a nonlinear inductor. You have these higher terms. And then what actually happens is that this ellipse deforms to kind of banana. But if you just want to amplify the signal, you don't care so much about it. If you want to modify the vacuum fluctuations here by like sending squeezed light, this is a very big problem. Yeah? But for the amplification purposes, we can ignore this effect to some extent and then go to amplification of about 20 dB. Right. So the point of the squeezing is really that you don't add noise, but the price. Yeah. You de-amplify. So and you amplify here. So the price to pay is, of course, you cannot reconstruct your signal anymore. Yeah. But the thing is, we are not interested in the phase of our signal because we know the phase of our signal. The phase of our signal is determined by this first pi/2 rotation. Yeah? If I rotate like this, the signal will be here. If I rotate like this, initially the signal phase will be here. So I know the signal phase. So I can rotate my ellipse, squeezing ellipse, such that I will just get this signal. So this is the trick. And this is a photograph of the setup. So this is how this quantum limited EPR spectrometer looks like. It's a dilution fridge. Here's a 4K plate, then the still, and this is the mixing chamber on 2 stages. Let me zoom in. So this here is the actual EPR setup with a 2-axis Helmholtz coil, and then inside this box we have these chips. And on these chips are the EPR resonators, and there are 3 of them. So this is nice. They are small, so we can pack multiple of them. Can have multiple experiments at the same time. And so this is how they look like. You have the capacitor, and then in the middle, this is the actual active region for our experiment, which defines our mode volume, magnetic mode volume, and this is in this case 100 micron long and 500 nanometer wide aluminum wire. So if you make this wire even smaller, you can boost the sensitivity even more. The other ingredients is, of course, the Q factor. So we work typically with Q factors on the order of 100,000. And so this is a V-NA trace in reflection, what you see there. Yeah. Yes. So the 3D cavity is basically is to shield. Yes. So the resonance frequency of this 3D cavity is somewhat 8.5. And what this does is, so these structures here would normally just radiate away microwave radiation. And by putting that in this 3D cavity, which is not on resonance, we basically engineer the electromagnetic environment, therefore suppress this. And basically, by changing the length of these coupling antennas here, we can actually tune the coupling. So we can have the same chip and tune the coupling to our resonators to go into different regimes, which makes this approach quite flexible. So in principle, we can go to like 400 millitesla. As you will see, we don't need that field for the moment because we're looking at a very special system. And we're working with aluminum at the moment, so we cannot go to very high fields. Yeah, that's correct. And of course, the limitation here is clearly you cannot sweep quickly because you induce eddy currents, but we don't need to do that. So this is the design choice we made. This box here actually is the parametric amplifier, which also needs to be at millikelvin temperatures, of course. And then the next amplifier sits here. Okay, so this is the scheme roughly. So we have an input. The signal, so here we send our pulses, the signal reflects off these planar resonator structures. They talk to the spins. The signal, which contains just a few photons, microwave photons, comes back, is amplified here, and then goes up, gets another 40 dB boost at 4K before it goes out to room temperature and is digitized. And these attenuators here are used to thermalize the system so that basically the signal to noise of the input signal, or that the input signal does not add noise to the system, of course. Okay, so about the spins. So what we are working with is a kind of model system to test this. In the lab, we're working both with bismuth donors and silicon and NV centers. So here we'll only talk about bismuth. So essentially the bismuth is a donor in silicon, so what it does, it replaces a silicon atom, and then at room temperature it gives away his additional electron to the conduction band, but at low enough temperature it will trap the electron, and then what you have is some sort of like hydrogen-like system. You have the wave function of the electron is somewhat S-like, and basically it's this electron spin we want to probe. An additional feature is that the bismuth has a 9.5 nuclear spin, and we have a quite strong overlap, so we have a very strong hyperfine interaction, which gives rise to a zero field splitting in the 7 gigahertz range, which is very nice for superconducting circuits because we don't need to apply a lot of field to tune it into resonance with our resonators, which are also in the gigahertz regime. So it's an interesting system to play with, and in addition, since we are working in an isotopically purified substrate which has no nuclear spins, we can work with long coherence times. Okay, so this is then the sample. So the spins are implanted here just 100 nanometers below, and this is then the active region. And the experiment is essentially simple. You just apply, as you saw it in the cartoons before, a pi/2 pulse, you wait, then you apply a pi pulse to rephase the spins, and then you record the echo. Note that the echo is very, very small compared to the driving pulses. Another feature you see here is that you see these ring downs. The actual pulses are just a microsecond long, but then because of the high Q of the cavity, you have the ring down, which makes the pulses much longer than they actually should be, and gives rise to this deformation. The blue line here is a fit to the theory, and there the only free parameter is the number of spins. So with this we can extract the number of spins which contribute to this echo, and so we find that it's about 250 spins which contributed to this echo with about a signal to noise of 1, and then if we compare that to the 10 to the 13 spins you have in the commercial spectrometer, this is a substantial improvement. However, this does not help you a lot if you cannot repeat the experiment, yeah? Because normally what we do in the lab, we repeat experiments to acquire more and more signal. But now we are at millikelvins, and at millikelvin temperatures in these very pure systems, the T1 times can be very, very long. Yeah, and just to give you an illustration, so after the manipulation, the spin decoheres, we need to wait for it to relax to the ground state. And how can it do this? It can emit a photon, it can emit phonons. The problem, normally the spin only relaxes through phonons, but at low temperature all these phonons are frozen out, so it just sees a phononic vacuum. Yeah? And free radiation and free space is basically a negligible phenomenon, as Andrin said. So what comes to the help is actually that we have these strong couplings and these high quality factors. And what this does, it gives rise to this Purcell effect, and it actually enhances the radiative relaxation. And this is a very simple formula. You see, this is the resonance frequency of our spins and cavity, and if you are on resonance, you have the coupling and the quality factor, which will actually shorten our T1. Yeah, and just to give you an idea, this is a measurement from Audrey Bienfait. If you are detuned from the resonance, so you switch off the Purcell effect, you get T1s on the order of hours. But if you are in resonance, you put that down to 1 second. And now with our new designs, we can actually boost that to 20 milliseconds. Yeah, so this gives us a huge improvement. So we can repeat very fast, and now we can actually measure 65 spins per second. So the 65 spins per root hertz sensitivity. And our ultimate goal is to go to 1 spin. So what you have seen so far, cavities are great. Everybody knows cavities are great to enhance the signal, but they also cause problems. Yes? So I didn't show the T2. The T2 is on the order of 2 milliseconds in this sample. So, but anyway, the T2 would always be T1 limited. Well, it's not a Ramsey measurement because we have the large inhomogeneous broadening. We cannot measure T2 star, but we measure like the spin echo. But for this you need coherence, you need phase coherence. Yeah? And you can only measure so long until this coherence is lost, which is expressed in the T2. And after that, you cannot do anything to the system. You have to wait until it relaxes to the ground state so that you can start with 0 phase again. Right? You need to reinitialize. And what this does, it initializes your system. Yeah. So cavities are great, but they also cause problems in our measurements because we are driving the spins through the cavity. So, but the cavity has a bandwidth. Yeah, the cavity is a bandpass filter. So what it does is, ideally we want to drive the spins instantaneously. Yeah, you want to make these rotations in no time. And so what we do, we apply like these 1 microsecond pulses, but then what happens is that this pulse gets distorted, yeah? So basically the field rises slowly in the cavity, and then the field stays in the cavity and leaks out slowly. So this is what you see here. And this way, we cannot really precisely drive our spins. And the other thing you see is also we need a minimum separation of our pulses, so we cannot really measure short T2 times here because we need to wait for this driving to finish. So how to solve this problem? We can since this is a linear system, yeah? A filter is a linear system, so what we can do is we can just deconvolve the cavity response. So, and basically by just compensating with our input field what the cavity will do, we can actually erase this decay here and achieve pulses with a bandwidth which is shorter than the cavity bandwidth would normally allow. And here you see a measurement of the intracavity field. Here, this is the pulse areas are basically the same, but you see here if I use square pulses in blue, it's spread out in time, whereas if we use the cavity compensation pulses, we get nice delta-like driving pulses. And this opens up a lot of possibilities because, well, actually the one thing before I come to that is actually, since we now drive the spins more precisely, they will rephase also in a shorter amount of time, which will increase the signal per unit of time, which also increases the signal to noise, because what is our echo signal? Our echo signal is the integral over the signal. So if we integrate over a shorter amount of time, we acquire less noise. So this, just for free, enables us to reach better signal to noise, actually. So this opens up a variety of new possibilities. I don't want to go to details, just flash this here a bit. So since you are able to remove the free induction decay, the leakage of the cavity, the ring down of the cavity, you can actually look at physics that happen inside this. So normally the ring down of the cavity is much longer than the FID of the spins. Yeah, we have, in our case, we have very broad ensembles. So the ring down, this FID, is very quick. But now, since we remove the cavity field, we can now switch on our Josephson parametric amplifier directly after the pulse, yeah, and then see actually the FID decay through the cavity. So the spins, it's normal in exponential decay, but the spins also have to talk to the cavity, so they build up cavity field, and then this leaks out. So this is the FID of the spins, and this is the simulation of the signal. The second thing is, of course, now you can also do this dynamically decoupling sequence, the CPMG sequences, and since your pulses are shorter, your echoes are shorter, you can pack more pulses in a short amount of time, which allows you to cancel higher frequency noise and also accumulate more signal to increase your sensitivity. So here you see 1,000 pulses in 10 milliseconds. And the last thing is, you might have noticed that there's like a difference in the shape of the echoes compared to the square shape. And now that we apply, so you have to see, our cavities are very narrow, and our spin line width is much larger. And if we now have a pulse which has a larger bandwidth than the cavity, we address a much larger bandwidth of spins, and so then the spectral shape should be reflected in the echo shape, because they are related through Fourier transform. So what you can do is, still, this signal still contains the cavity transfer function, but this we can remove. We just divide through the cavity transfer function, and then we get actually the spectral shape of our spin ensemble. And the black line is just a simple model. So what you see here is we change the repetition time of our experiment, which means we change the polarization of our experiment due to the Purcell effect. We just give the experiment the spins less time to relax. And now, what I haven't told you is, of course, the Purcell effect depends on frequency, so it falls off quadratically with frequency. So for spins which are detuned, they will relax slower. And this is basically reflected in this shape, so which then is reflected in the polarization. So you have a detuning dependent T1, and this is what you see here. And this is a very, very simple model, but you see, like for most repetition rate, it nicely reproduced the data. Good. So now, since we have this very nice pulses, and the good sensitivity, we can think a bit about applications, so where to go with this. And in my remaining time, I just want to show you a nice example of what we can do. Because with this spin sensitivity, we can now look at, for instance, two-dimensional systems which contain very few spins. And one thing we do here is we use our sample. Our sample is this bismuth donor in the silicon, and we have isotopically purified silicon-28 to remove all the nuclear spin, but the purification is never perfect. So there will always be some silicon-29 spins, nuclear spins, which have a spin 1/2. And so the concentration by our supply is 0.05%, and we actually manage to see them. And what we do is, so this is the spectrum, we go to very low field, and since we have this large inhomogeneous broadening, we have actually spins everywhere in our spectrum, which is great because now we can study the nuclear precession frequency as a function of field. And so the measurement is rather simple. You go to very low field in order not to suppress this dipolar interaction. And what you see here is you see basically T2 decays measured with spin echo. And what you see at this low, very, very low field of like fractions of Gauss until a few Gauss, you see these oscillations coming up. If you Fourier transform, you will find that they correspond to the gyromagnetic ratio of the silicon-29. And now by fitting all those curves for different concentration, we can now actually extract the concentration of these silicon-29 spins. And what we find is that the concentration is on the same order as described by our supplier. And what we're talking to here is the spins, about 100 nuclear spins talking to one bismuth, and the whole signal comes from about 500, 400 bismuth spins. So just to illustrate this a bit. Right, and this I just want to flash, so that the problem here is, of course, you see, we are very limited by T2. We go to very low field, so that the oscillation of the nuclear spin is very, very slow. We're talking about kilohertz or sub-kilohertz. And despite that we have 2 millisecond T2, we cannot really resolve nicely all these oscillations. And then you go to a standard EPR book and you look what better pulse sequences there are, and then you get to 3 and 5 pulse sequences where you just store this interference basically in population. You wait some time and then you bring the electron spin back onto the equator, so you have some sort of interferometer, and so then you interfere the electron spin with the nuclear spin evolution during that time, and then you're just only limited by the T1 signal, and then we can resolve much better oscillations and get a much better Fourier transform of our signal. And what I want to demonstrate with this, like using these optimal control pulses which do the cavity compensation, now we can basically apply all these techniques which are well developed since, like, I don't know, the 60s, the 70s in EPR, so we can now benefit from all this knowledge to apply them now in this high sensitivity setting. So to finish, of course we want to go to higher sensitivities, and I want just to flash how we are going to do this. So we have a poster of Vishal Ranjan. He's going to continue the project, and the way to do that, so one way would be to increase the Q, but we're at the moment at the limit of what we can do with our fabrication. So what we are going to do next is we will make these wires much smaller. So I had 500 nanometers diameter, and now we're going to 25 nanometers and just 1 micron length inductors of our resonators, and that will provide enough coupling strength so that we can reach the regime below 1 spin sensitivity. And the ultimate goal is, of course, to put a single biological molecule and then do really single molecule EPR in this setting and just detect the inductive signal from the spins. So to conclude, I showed you the 3 ingredients, how to boost the sensitivity of a conventional EPR spectrometer by going to low temperatures, using superconducting microresonators, and employing a quantum limited detection chain, and with this we reached 65 spins per root hertz. But this is not the end. It's quite clear how to go to 1 spin and maybe below by making the structures even smaller. And then I think the system is now actually ready also to be employed in some real-world application where we look at, with already the present sensitivity, 2D surfaces, fundamental materials, for instance, or graphene or whatever. So I think there's the whole zoo of applications which were not accessible with standard EPR techniques. And crucial was this cavity compensation. And I just want to acknowledge all the group members and my collaborators, mainly Patrice Berthet, who is the PI of the project. And yeah, so with this, I'd like to thank you for your attention.